students. So let's keep talking about how to solve our two-dimensional heat equation, 2D heat equations using finite difference method, specifically using our MATLAB. So that's what we're practicing in this lecture 8 specifically. So we are following the steps I made for you here. So what we had to do to use MATLAB, we had to convert all the equations following the MATLAB language rules. So we did it in step 1. All right, so we did it. And then this bold box will be our solutions MATLAB will provide us. So our scheme for our solving was finite difference method scheme. So for that one, we had to divide our domain into the number of grids. Okay, so here for this one, to divide our domain into the number of grids we're going to decide, we had to first define our geometry of the domain to the MATLAB. So that was our step 2. And then step 3, then we can define number of nodes. How many number of nodes, how many number of grids we will have in those two x and y directions, because our equations in two-dimensional space. Then we did it. So depending on the number of grids, our solution can be more accurate or less accurate. We do know that one. So we're going to compensate depending on the accuracy level versus calculation time level. That was step 3. And then we can actually make grid size once we do have domain size, which are the width and height in 2D, divided by number of grids for x and y direction for width and height respectively. Then we can let MATLAB know what will be the grid size in our calculation. MATLAB don't know if you don't command this one. We have to at least let them know about this sentence. So that will be arranged by step 4. Okay, we did it. And then visually, we defined this delta x and delta y to the MATLAB. Again, students, keep that in mind. These steps are arranged for MATLAB calculations. Okay, MATLAB calculations. And then step 5, what we have to do, now we have to create an array for our solutions, because here we do have a domain. Let's assume we do have a rectangular domain for our heat transfer problem. So here we created so far grids here. Okay. So here, every these grid, we will have a solution in terms of what? Temperature. Okay. So this is a grid, but mathematically, this is an array. So this size, grid size, will determine the size of our array matrix. Okay, matrix. And then in this matrix, this node number will be the element, individual element will inside this matrix. Okay, in terms of mathematics. So here in step 5, we are gonna let MATLAB know what will be the array we want to create. Okay, and then we are gonna assign the node numbers. That's what we did. Temperature information, all right, will be there, but here at the boundary, it's given from our scenario situation. Okay, so that is why for our array, we're going to start from here, that's node number 1, but we have to start from number 2 right next to the boundary. Therefore, n of x minus 1. Same for y directions as well. So we assigned the node numbers for that array we created. And then we have to also let MATLAB know. That's what we did. And then here, we moved to now to the initial condition. So we created ny by n of x size of matrix, right? We did it. And then we have to put the initial conditions. Since the current problem is a steady state problem, therefore steady state means our solution will not change in time. Therefore, it is truly independent of the time concept. So in this problem, steady state problem, we are super free to assign initial condition. So we can just choose a random number, then our solution anyhow will be converged with given any initial conditions. So we're gonna just put a random number here to start our calculations. Okay? So here, mathematically, what we actually can do express, since we are dealing with now initial conditions, so at time equals 0, our calculation didn't start. So therefore time equals 0. So row means starting from n to the ny, right? That's the row. Therefore n to the y, this is a row and column. Okay? So therefore all lines will be filled with the initial conditions. So we're going to assign the numbers using initial conditions, but that will be arbitrary number for the steady state. Okay, arbitrary state number. But if it is a transient problem, we do have an initial condition because a domain was exposed time equals 0. So they will have their certain number in terms of temperature. For example, all are 20. So here is also 20, 20, 20, 20, 20, 20, 20, all 20 at time equals 0. Then this guy was exposed to the certain environment. For example, it just heated from time equal 1. Time equal 1. This heat was applied to our domain. Then we do know temperature will increase anyhow. Then what will be the number inside of this domain? So at time equal 1, then this will be 20, but this will be 21, 21, 21, we don't know. But we can calculate. But number will change from initial condition. Does it make sense to you? That's the initial condition concept. But the steady state, time is not included because it's just temperature is not changing. Temperature is not changing in time. That's a steady state problem. Therefore, temperature, but we need to calculate this problem. So what we're going to do, we're going to just put the random number here. Put the random number you like. So MATLAB can start from that number for our problem. Once you did, then it's a time to deal with the boundary conditions. So we filled all the elements in this matrix with a certain number you chose as the initial condition. But for here, that's true. But boundary, no. We have a certain specific boundary conditions for this problem. So means we have to consider the boundary condition effect. Therefore, we're going to deal with now boundary conditions. So express your boundary conditions for the given situation using finite difference method. Because your boundary conditions also must be expressed using finite difference method scheme. All right? And then also keep that in mind. Our expression also must follow the coordinates in MATLAB. Especially for the step 3, we're going to practice more details through the next page. How to express the boundary conditions using finite difference method. Okay, we're gonna make 4 common scenarios, and then we're gonna express those boundary conditions using finite FDM scheme. Okay, no worry. Once you did, it's the time to solve. Okay, MATLAB is ready. Okay, MATLAB is ready. Okay, run the finite difference equations. Okay, then MATLAB is ready to solve that equations using FDM schemes, and then solution, which means the temperature information for each element here. So each element we assigned, we will get the information from the MATLAB. Once we have that data, also we can plot using MATLAB. So let's also visualize our temperature field from our results. That will be the steps. Okay? So we need 9 steps in MATLAB. Okay? Follow that one. Okay, that's it. So you're gonna do these 2 steps, okay, in your design project as well, to solve the given problem, the given equations, and then make a visualization, make a plot, okay? So to get the plot and then to get the solution, you will apply these 9 steps, okay, using MATLAB. It will work. Okay. I'm gonna turn off my video, the email. Okay, popped up. All right. So here, next page. Okay. Only thing we need to do a little bit more, like practice, how to express our boundary conditions using FDM scheme. Okay, using also still following MATLAB coordinates, because we're gonna use these MATLABs. All right. So for this one, okay, students, what we're gonna do, we're gonna make these common scenarios. First case, constant temperature. Our boundary conditions will have just a constant temperature. It's like left 20, right side 20, and top 100, super hot, and then bottom is still ambient temperature 20. Then what will be our temperature field? I already did write my MATLAB code, and then you see these plots for each case. And then you already see here through this work, you see temperature fields depending on boundary conditions are completely different. Completely different. You see that one. That much boundary conditions are important to determine the solution. They really govern our solutions. Makes sense, right? Makes sense. Okay. So let's go back to the topic, how we can express our boundary conditions in FDM following our MATLAB coordinates. Let's talk about that one. Okay, students. So here, so first of all, let's make index here. So this, because this we are solving our problem following our common general coordinates. Starting from left to the right horizontally, we are using that one as x coordinate. Starting from bottom to the top vertical direction, that's our y coordinates in this common world. So therefore, for the indexing wise, we're going to start, but still we want to use MATLAB, and we have used the MATLAB, and we are here in step 7 to express our boundary conditions, okay, in FDM scheme. So therefore, our number, MATLAB, always first element starts from number 0 in terms of index. So following that one, it will be number 1, index 1, not 0. Okay, and then go to, because we decided we are going to have n over x grid size for this horizontal direction. Yes, so therefore final index in horizontal direction will be n over x. Similarly, vertical direction, we decided to create the number of grids up to n over y. Therefore, index, final guy will be n over y. And then what we want to do for the boundary condition here, okay, let's start from, because we are dealing with the 2D domains, so we need 4 sides for 2D domains, right, which are the left and right and top and bottom in terms of boundary conditions. Okay, let's start from the left side. How to express this left side boundary condition here? 20 degrees Celsius. All right, this is temperature, right? Temperature. Okay, so for the left side, students, left side, I'm gonna delete this red color circle, yeah, to be clear. So left side here, okay, temperature, okay. So here, students, always, since students keep that in mind, we're using MATLAB. So our coordinate must be MATLAB coordinates. So here, row and column must be filled here. So starting from row. So here, Y, row. So all row, right? All row of the left side, in terms of MATLAB language, all means this column, right? Column means he will read every here point in this vertical direction. But it must be column-wise, it must be only number index 1. Yes, just read that one. That means what? Who is this guy? This will be the left side, this guy. That one must be only filled with number 20, because that's the temperature of our boundary condition of the left side from the given situation. Is it clear? Once you are clear with this, other side, other 3 sides, same logic. Again, let's move to the right side, right hand side here, boundary, still 20. All right. Then how we can tell this condition to the MATLAB? Okay, MATLAB, temperature, read all raw, okay, all row, therefore column, but it must be whom? Column wise must be this guy, n of x. For that array, please fill with number 20. Okay? Then your array will be 20, 20, 20, 20 for this guy, left end. Okay? Then 20, 20, 20, 20 for this guy. Boundary condition. And then here, certain numbers will be there. Initial condition was filled. Does it make sense to you? Do you see I'm keeping space here for the top and bottom boundary conditions? And then here, let's move to the top boundary condition, students. Top boundary condition. Top, same logic, temperature. Okay, here. Okay, students, top means whom? Okay, I'm going to use again red color, top, this guy. Okay, top, this guy. So starting from, okay, so this one, only in terms of row must be whom? This n over y. Does it make sense to you? So it must be read only n over y, but any column must be all here. So therefore read all the row for the n over y column, then filled with 100, because that's the top boundary condition. Similarly, if you understand this logic, same for the bottom as well. So bottom, if then it will be again temperature. Okay, only read this row, which is 1 for all the column, that must be filled with 20. Okay, that will be the FDM expression for the constant temperature boundary conditions. Once you type this one in step 7 to the MATLAB, okay, then plot it, then this will be, you see that one? This will be the result. At the end of this lecture, I will turn on my MATLAB code and then I will show whether it was true or not. It's true, yes. I will show that on my MATLAB simulations as well. Okay, so let's move to the next scenario. Okay, so here we do, what if we have insulated surface? Especially at the left side, we have insulated, then other sides are just still constant temperature. Then how we can express that insulated surface at the left side? All right, we know what the insulation means in terms of heat transfer. What is insulation in terms of heat transfer? No temperature difference at the surface because no heat transfer. No heat transfer means no temperature difference. All right. We're going to apply that knowledge to express our insulation surface boundary conditions at the left side. We have domains here. Our indexing starting from, again, 1 because we are using MATLAB. Okay, then next node will be 2 in terms of index. And then end guy will be n over x. In the vertical direction, again, starting from 1, and then left guy will be, the end guy will be n over y. All right. So other sides are same constant temperature. Therefore, we can just use the same way we did in this first scenario. But the left side is completely different because it's insulated surface. All right. So if then insulation, no temperature difference at the surface, left surface. If then, students, temperature at this surface. Temperature at this surface at index number 1 in this column means read all the rows you made in terms of grid, but column only number 1 index, that temperature must be same with the temperature right next to the column. Because there is no temperature difference in terms of this one. Because our index in terms of temperature will only start from number 1. Right? So therefore, we are going to use this right next to guy to express insulation because there is no temperature difference between them. That's the boundary insulation meaning in terms of heat transfer. So if 1 and 2, this small index, the distance of the right neighborhoods, there is no temperature difference, that means insulation. And then this figure, this graph plot shows the results from that one. Completely different temperature field compared to the previous case. Okay. So here, students, look at this. Okay. Do you see that one? Insulation temperature difference is not there. Do you see the slope temperature gradient at this boundary is 0? Yes, because insulation. Temperature gradient is 0 there. Means no temperature difference. That means insulation. If we see also, students, the first case here, heat always flows where to where? Hot to cold. Hot here in our scenario, it was 100 degrees Celsius, and then bottom 20 degrees Celsius. We do know heat will flow top to bottom, but still it is 2D problem. Heat also can can be losing to y direction. That is why it also flows like this. Okay. So see, do you see the yellow 100 and then cold is 20? So here still hot, but temperature field will like this. Do you see that one? What if we do have both the sides in this left and right sides insulated? All right, how we can express? Let's practice one more time for this scenario. Left, the same way. So here, let's clear with let's make it clear with our indexing. So 1, starting from next guy will be increasing number 2, and then n the guy n over x, because you made n over x size of an array in terms of degrees, and then therefore right next guy will be n over x minus 1. In vertical direction, you decided you're going to have n over y size of degrees. Okay, so let's deal with the left-hand side. Left side wall is insulated. How to express this insulated wall in terms of an FDM scheme following MATLAB coordinate? All right, insulation means there is no temperature difference at that left side wall. Okay, if then it will be, okay, temperature, all this row in the column index number 1 must be equal to temperature all the row of column 2. There's no temperature difference at the surface. Okay, at the surface. Insulated, we made that one. Then let's move to the right side, which is this case. Then how to express? Alright, then temperature, again, temperature. Read all the row at the index number n over x. Read all the row n over x column must be equal to just right next to neighborhood. There will be no temperature difference. X minus 1 column. So means we express this right-hand side also must be insulated. Then students, this will be what? 1D steady state problem. 1D steady state problem. Top is hot, bottom is cold. Heat will flow from top to bottom. Temperature is not changing in horizontal direction. It will only change in vertical direction. 1D problem. Okay? Because the temperature is insulated at right and left sides both. Therefore, heat only will flow top to bottom. Lateral direction, there is no heat transfer. Does it make sense to you? The last case, okay, we can make in terms of a boundary condition will be what if? What if our one of the surface or surface is exposed to the moving fluid? Students, moving fluid means convection heat transfer. We talked about that one in the boundary conditions, right? Previously lecture. We do know that one. So what if our surface, our boundary, is exposed to the moving fluid? How we can express the conditions in FDM scheme following MATLAB coordinates. All right, we know how to do. All right, so here, let's do that one if then. Always starting from what? Take a control volume at the boundary. That's number 1 step. Then step 2, apply energy balance to the control volume. That will give you an expression, mathematical equations. All right, so let's do that one. So here, what I made this scenario here, top surface is exposed to the moving hot fluid, having this condition. Okay, then left side is insulated, and bottom and right side having constant temperature as 20 degrees Celsius. And then other cases, we do know how to express. Okay, we do know how to express. We do know this one, we do know this one, we do know this one. But how we can express this top surface? All right, one more practice, students. Insulated for the left side. Insulated means there is no temperature difference. Okay, there is no temperature difference at the boundary, left side. Okay, again, starting from indexing, number 1. Okay, number 1. So forget about this 0. This is a typo. It must not be there. So number 1 and then number of x. And then we do have a number of y. Okay, number of y. And then right below number of y, it will be number of y, n of y minus 1. All right. So left side insulated, temperature will be identical with here. All the row for number 1 column must be equal to all the row for the number of 2 column. Okay, here this side, temperature must be identical. Then we can say left side the left side is insulated. Then let's deal with how to express this top surface exposed to the hot moving fluid. All right, so what we're gonna do, if then we know how to approach. Take a control volume at the top surface. And then let's see energy flows there. Okay, energy flows there. Students, thermal energy, which is heat. We do know heat always flows hot to cold. Who is hot? Hot is here, this guy. And cold is relatively cold is this guy. Therefore, heat will flow from outside to inside for sure. Yeah, for sure. Then following which heat transfer mode? That's the next we have to determine. All right, heat in from whom? Moving fluid, therefore convection. Okay, and then heat out to the control volume here will be heat out from the control volume will be in the domain already, therefore it will be conduction. Oops, does it make sense to you? So do you see that one? If I touch this, my touch screen is very sensitive, so it just popped up during my lecture. All right? But since we are following energy conservation of energy, students, therefore energy must be conserved. Therefore energy in must be equal to energy out by energy balance. All right, so in this control volume, energy balance must be valid. Therefore, energy in from convection must be equal to energy out by conduction. Convection heat transfer, students, Newton's law of cooling will be there. So since it is heat flux, we don't need to deal with surface area. A will not be there in our equations because it is heat flux. So let's start from the convection, Newton's law of cooling. H multiply what? Temperature difference. All right, so H convection convection coefficient is given from the problem, which represents the characteristic of the moving fluid. It's given, it's a property. Then temperature difference. Okay, temperature difference. Okay, temperature difference, hot minus cold. And therefore, here students, it must be T from the hot fluid temperature minus this temperature. Does it make sense to you? Rho column. So we must read this guy. It will be n over y, then all the column. Row, again, row, column. Following MATLAB coordinate. So row, n over y, row, and then all the column, that will be top boundary condition. That must be equal to conduction, heat out. Conduction, students, again, okay, thermal conductivity according to Fourier's law, K multiply A, we don't need to because it is heat flux, K multiply what? Temperature gradient. Temperature gradient. So we do have delta Y, students. The delta Y from the grid side, okay, that will be the heat transfer, the distance, okay, that can be calculated by delta Y. And then that will be denominator, then numerator will be temperature difference. So temperature difference can be calculated at that boundary, can be calculated by whom? Temperature at the top, n over y, and then right next to guy, n over y minus 1. Right below guy, this guy, temperature. That will be the temperature difference at the boundary. And then, this is not the things you really have to express. Yeah, that's the energy balance. But for the MATLAB, you really have to express, okay, then what will be n over column, this guy, will be n over what? N over y. Oops, do you see this one? Okay, n over y. Okay, what will be this is a boundary condition because that's what we want to express for the top. Okay, what will be temperature at the top surface? What is the boundary condition? It will be like this because you have to rearrange. Okay, this one is this one, and then put all other terms to the right hand side. That will be the top boundary condition expression. Sorry, does it make sense to you? And then once your top surface is exposed to the moving hot fluid, and then left side wall is insulated. Do you see here? Insulated, temperature field in your domain will be like this. Okay, that's it. So according to the lecture 7 and 8 you learned so far from these lectures, you're going to fully apply this knowledge to your design project. Okay? So design project will be posted today, and then you're going to start the work with your team members. All right? Okay, students, this is about lecture 8. Thank you.